The last few slides, I think I missed. Yeah, I mentioned about socket. I mentioned about how to use the socket code. Okay, and also some example on TCP. How to initiate TCP and also UDP. Okay? So the example that is given inside the slide. If you are doing some assignment related to that, you can actually refer to this or you can go to the website to find more information about how to program the software. In case some of your assignment might require this. Okay, I also talk about pipe. I think I touched a little bit on the pipe last week, maybe it's a bit rushed. Perhaps I start from here again. So if you use socket, you can not only use it for a program that is running on a different computer, you can also use to communicate between processes that are running on the same computer. Okay? But of course, it's not so efficient because TCP is meant for network communication, right? So from computer to another computer. But it does not prevent you from using socket communication using TCP or UDP for processors running on the same computer. A more efficient one is to use pipes. Okay, pipes is just like a pipe there, you pump in water from one side and then you receive from the other side, you can just imagine that. Okay, so instead of thinking about water, you can think about message that you pass it there, and then the receiving side, you receive it. Pipe is only one direction, just like TCP or UDP is also one direction. So if the person who is, the process that is sending the data into the pipe, it will come up from the other side, okay? And this process cannot send in this direction, you have to create a new one. So you need two pipes in order to have two-way communication. So why this pipe is good is actually to allow two processors running on the same computer to communicate with one another. I think this is more efficient, okay? In terms of maybe speed and also processing time. The speed and processing resources. Okay, and there are different types of pipes. If let's say the process have multiple tracks. Okay, maybe I introduce some terms because you see processors, you also see tracks. What is the difference? the term process, you also see the term threads, and they look alike. Actually, they are quite similar. The only difference here is this is heavy. Heavy, that means it has a lot of baggage. This one is light. Okay? Why is it heavy? Because it contains all the contacts, and the contacts contain the information about the memory, information about the privilege, the information about resources that it holds. Okay, resources that it holds. What else? Memory, privilege, resources. Actually, memory is part of the resources. And here, it doesn't have, it has context as well. Apart from it, it has the runtime context. Okay? For this, no, it doesn't have that. It doesn't have all this. It only keeps runtime context. Okay? So it's light. It does not carry all this. Now if you create a process, it's quite heavy. It takes a lot of time to create it. Thread is light. When you create it, you create faster. Okay? So these are the most distinct differences. Okay? What are the similarities? The similarity is it can do multitasking. Multitasking. Okay, so this is similarities. Okay, not only process can do multitasking, both can do multitasking. Okay, I think here I need to put some here. Switching is slow. Switching is slow. Okay, here switching is fast. What do I mean by switching? You touch, process switch and task switch, or thread switching. Let's say, for example, one thread running, and then you want to switch to another thread, then it's fast. This one, when you switch from one process to another, it will be very, very slow. Okay? So there is some similarities, there are some differences. The differences is this. The similarity is they can do multitasking. The purpose is usually multitasking. Okay, and also another difference is this, which is number 4. Okay, number 4. This thread here actually run within the thread. Run within process. Okay, it doesn't run within any process. Okay, so this process is actually itself. The thread, it cannot stand alone. It must be run within this process because it doesn't have memory, it doesn't have memory. So you have to run in a process which the privilege and the memory and the resources actually come from the process itself. So you can imagine one process can have multiple threads. Understand? Okay, the process, among the process can do multitasking. Within the process, you can multiple thread which can do multitasking as well. Okay, you can just imagine that. Alright? Now this pipe actually, one thing good about this pipe is it's not just for thread to communicate with one another. In fact, we don't use pipes to communicate with this thread. We use another way to do it, although you can, but we don't use it for here. We use it for process. So imagine that if this is one process, this is another process. Then we use pipe to communicate between them. Okay? Within the process, we have threads, and this thread can communicate with one another. Normally, we don't use pipe, we use another way. I'll show you later. Okay, so these pipes we have two different types. One is ordinary pipe. The other one is named pipe. Okay. So within the process, you can have multiple threads, right? So if you create a pipe, you don't need to give it a name because the process itself knows what is the pipe, and then you can pass to this thread, this pipe using the reference. Maybe something like this. And then you got a pipe, and then you have a pointer, let's call it P, and then here is create pipe. Let's say. So you create a pipe, and you have this pointer pointing to this pipe, and then we pass along this P to any of the threads. So this thread can actually communicate with one another. So this pipe that is created has no name. Okay? Okay, so and it's unidirectional. That means like what we've seen before. We can use it for standard. It's actually a standard producer-consumer mechanism, and I'll explain this what it is. It's just saying that pipe is actually a standard for producer-consumer. I explained that later in chapter 4. And it has a parent-child relationship between communicating processes. If you are using processes. Okay, you can have parent, and this parent can actually create a child process, and then you can create pipe so that they can communicate with one another. Okay? Or this is a process, this is another process. They can communicate with one another as well, like this. Okay? But if this is a child, then you can pass this ordinary pipe without a name to the child. Okay? Just pass along this. But then when you share between these pipes, you do not know what pipe it is. Right? You cannot share this. Because if you're able to share, you must have able to communicate in the first place. But how are you going to communicate if you don't have the pipe in the first place? Right? So between processes, they have to use name pipe. Okay? So how does the name pipe is created? You create a pipe just like this also, but it has a name. Okay? And this pipe will appear in the directory. Okay, appear just like it's just like a file name, right? Okay? And then a file, any process can open a file, right? Even though they're not related to one another. For example, this is a child of this process because this process creates this child process. So it can pass. When you create the kind, you can pass the information and you can pass this ordinary pipe without name. But then between these two processes, which maybe this one is Firefox, this is Google Chrome, for example. I open this and open that. So neither of them creating one another. So they do not know one another, right? So how do they get the same pipe to communicate? Right? If you use an ordinary pipe without a name, then it's impossible because you need to pass that along. You cannot pass it. Okay? So in this case, if we use name pipe, when you create it, you will create it as just like a file in the folder. So it's visible to all processes. So the process must go into that folder to open that name pipe. So once you open, then they can communicate with one another. So name pipe is just ordinary pipe with a name, and it appears in a folder. Okay, so that any program or any process that run can go to that folder and open it, and they can start to communicate. Right? Okay, ordinary pipe, you don't have to explicitly delete it because when you kill this parent process, the ordinary pipe will be deleted automatically. But name pipe is different. When you create it, you will create it as an object inside the folder. And you leave even though the process dies. Right? So you have to go and explicitly delete it. If you don't delete it, it will stay there forever. Right? So that is the pipe. And why we have two different pipes? The reason is because of this. The one that I mentioned previously. Okay, maybe you'll be wondering, if I create the child, right? How do I pass it? When you create a child, you do like this. You use a function called fork. you create a process by using this function called fork. Fork is just like the fork that you eat with a fork, right? And you see the fork has multiple prongs, right? So it just means that you can actually go either way. So forking is creating a child process, and here you can pass in the parameter. What do you pass in? Pass in this pipe. So this is an ordinary pipe without name, and you can pass it just like that. So you don't have to use name pipe where you create a file, and then you get the child to open it. Although you can, but the more efficient way is to use ordinary pipe, and you pass in when you create the child process. Okay? Okay, there are of course many other ways to do communication. Another way is to use message passing, and there are many variety of message passing. In fact, this part is also message passing. Okay, but right now I think this slide, what it's trying to say is about, just now it's not related to distributed computing or parallel computing, it's general. But right now we want to focus on distributed systems. If let's say we want to do communication, but we want to do it in distributed manner, you can use pipe, but it's going to be very tough. Why? If you create two processors, you want to communicate between them, you have to create pipe two ways. You create another one, you also have to create another pipe. Okay, you cannot share. Whereas this message passing interface is a library, it's just like OMP, but this is you're able to do it. You can do distributed computing and parallel computing over the internet or over the network on different PCs. Okay, OpenOMP is only for parallel computing for single computer. Okay, so message passing you can actually MPI you can use it for different computer. Right, so this is another way of doing OpenMP, okay, or parallel computing. All right, inside here, you don't have to create something like this. You just use the library, and it will handle everything for you. You create multiple process on the same computer or different computer, and you just use message passing interface, which is the MPI, and then you can actually send a message to any one of them. Okay, the library will help you coordinate and pass the message to the correct nodes. We will see some example later. Okay, in the message passing model, if we are using the MPI, this is, I think you're going to do it in practical 4 or practical 5, I can't remember. And the function that is provided is something like a send and receive. Okay, the sending thread or the sending process need to explicitly call this function send, and the thread that is receiving have to call this. If it doesn't call this, then this message will go into somewhere, and then you wait. You wait until the receiving end receive it. Okay, and how does the thread know who to take it? You see the ID there? Sorry, not this ID, this message ID. See this ID there? That ID is the ID of the thread. So you can specify who is the receiver. Okay? And also you can tag the message ID, okay? Which message that you are sending. Okay, so that the thread knows the sequence maybe, or what category the message is grouped into. Okay, MPI is a popular library which we will use later on. And this will allow us to actually create a farm of computers, just like what you see here, server farm. Okay, we don't have to buy one big computer, one massive computer to do all the processing. We can actually buy a computer that is off the shelf. They might have limited power or limited resources or limited processing power, but then we buy a lot of them, okay? And then we connect them together using the network is a connectivity plus this message passing system, then we can actually create a powerful signal system, okay, distributed system. So this is a popular software used. If you want to use it in your assignment, you can try this. Okay, for distributed system assignment. Okay, and the hardware need not implement the system-wide loads and store to execute the message passing because it's all handled by the library. Okay. So by using this, you don't have to spend a lot of money to buy supercomputer. You can actually buy commodity systems. That means very cheap computers. And then you want to do parallel computing, then you just cluster them together and then use this API to send the message or synchronize them together so that they work for certain goals. Okay? Right, so that is NPI. Now we are moving away from distributed system. I'm not sure why the slide is like this. Actually, we should talk about just now pipe and then it should come to here before it goes to NPI. Because NPI is a way to do message passing, but it's for distributed system. Right now, this is not just for distributed system. It's actually meant for this universal. Okay? Even though you don't have a distributed system, you can also use this remote call, procedure call, and what it is. Now, when you create a pipe, right, you have to physically, I have to create this pipe, and then I have to use this library. I need to know what library in order to send and receive the data using this pipe. Okay? The same thing for the MPI. I need to know how to send and receive the data using send and receive command or function like this, right? And some of us don't like this idea. Can we have a way that we don't have to worry about this? Right? I just want to make a function call, just like ordinary function call, and then it can do it for me. What I mean is this. If I have let's say I have a computer here that's running one process P1, this computer 1, this computer 2. There's another process that's running here, and then computer 3, another process, and they are connected to the internet. Like this. They're all connected to the network, right? Now, of course, if I want to use a TCP/IP, UDP, of course I can. I create the socket. Now I have to know how to use the socket, right? If I don't want to use that, because socket is very primitive, I have to create socket here, I have to create socket there, I have to create socket everywhere. So it's very tough. I use MPI, let's say, for example, right? If I use MPI, then I don't have to worry about this. I just tell MPI, this is one node, P1 is one node, I give the address. P2 is another node, I give the address. P3 is another node, I give an address. And I put it in a file. What is the node? Or maybe the name. And then the address. I pass it to MPI, MPI will manage it for me. So whenever the process starts to send message, okay, you look at this and then you send to the respective one. And each one of them will have an ID, we call it rank. And if I want to communicate with rank number 2, so I just say rank 2. I put it into the send and receive and then you get sent. And all is managed by the MPI library. I don't have to do anything, but still I have to call this function. So it's not so not like the way we program, right? We have to explicitly call send and receive. Is there a way that we can overcome this by not needing this? That means we don't need this at all, but we're still able to communicate. And we want to communicate transparently. What I mean is this. If, let's say, I have a program, and inside the program, what do we have? We have a lot of functions, right? Or maybe class methods, right? We got object, we got main object, and then we got methods inside the object. Okay, let's talk about functions first. So you got a bunch of functions, right? As you can see from my practical, I create a lot of functions and I call the function, right? Yeah? But I know that function is actually living in the same process, in the same computer, in the same process, right? And when I call, it's within this process, okay? But what if some of the function is not inside this process? It's on another process, or even worse, it's on another process on another computer. How do I call from here to here? If I want to call, I have to use this MPI, socket, or I can use pipe, I can use MPI, I can use socket, UDP or BCP, the one that you have learned. But you have to know how to actually communicate with them, right? So right now, is there a way that I can call this function inside this P1 just like normal call, function call? Okay? Somebody had to program it, right? Okay, actually you don't have to program it because it's there. You can use this. You can use this statement. Okay, the first one is remote procedure call. Okay, so let's say for example I have parallel add, for example, parallel add, vector add. I create a function here. Okay, and this one actually is inside P1. My main is inside here. My main function is inside here. And there's another app here, which is maybe parallel, find pi, the one that you have done. Okay, maybe this one use GPU, this one use OMP, I don't know. But you have main, and you want to call this. You want to call that. You can see in my main program, I just put the name parallel vector add and then parallel find pi. If I do that, in your imagination, it's only running on this P3, right? On the same computer. But if we use remote procedure call, this function can be anywhere. This computer can be in America, while this computer is in Malaysia, and then you call this function just like a normal call. And how does it do it? You do it using remote procedure call. Okay, there's a library to do that. Okay, what you need to do is you just register this function in this remote procedure call, and then automatically the compiler will create a stub. Create a stub. STUB. Okay, this stub is not a function. We call it name. The stub is just like a function that is residing inside your P3 with the same name. Okay, so your main will call this vector add, and that vector add is a stub. It does not have the code to process, but it has the code to communicate with this P1. Okay, and this P1 has another stub, and these two stubs is communicating with one another. So whatever parameter that you pass in here will be passed along by the stub, and then P1 will execute it, and whenever it returns, it will return to the stub and then back to you. So from your perspective, you're thinking that that function is living in this computer. Actually, it's not. It's living in another computer, just that you don't realize it. This is much better than because you don't even need to create socket at all, because the socket is done by remote procedure call by the stub. Okay, so when you register this function in this remote procedure call, you create this stuff automatically for you, and the communication between these two is handled automatically. Okay, you do not need to know IP address. You do not need to create socket. You don't have to do anything. But of course, low level, the remote procedure call will have to do it for you. You will need to know the address, the IP address, and you will need to know how to program the socket. All right? But from your perspective, it's just registering, that's all, and then you make a call. As simple as that. So this is much simpler to program, right? Okay? Now the remote procedure call, which RPC, it is for C language. Yeah? You can see the C language. Okay, I know that you might not know Fortran, you might not know Pascal. Anybody know this language? You know Fortran? Who know Fortran? You. What do you like? Fortran. No. Okay, Fortran is quite an old language. No more in use, but it might be used in banking or in some scientific community. Now, nobody uses it anymore. I think still people use, but not so popular. Pascal is even worse. And C is also not being used anymore. Everybody is going to C#, Java, and all that. Okay? So C is still used, but then it's getting lower and lower in terms of number of people knowing how to program in C. Okay, so remote procedure call is used for C. So it's a function just like this. But remote procedure call is not suitable for object-oriented program, just like C++, because you need to know class and all that. So in order to upgrade itself, then we have remote method invocation. You see the method here? This method is a class, object method. Right? So it means that this RMI is the same as RPC, except that RPC is for C language without object orientation. RMI is for object orientation language. It doesn't need to be C++. It can be Java, because Java is also object-oriented programming language. C# also the one. Also object orientation language. Anything that is not object orientation is remote procedure call. Any languages that support object orientation, they all use remote invocation, method invocation. Okay? Because this one is he has to know about class and all that, and a lot of data that is private and shared. Okay, so actually they're similar, except that depending on which language that you're talking about, and then apply the remote procedure or remote method invocation. Okay, so basically the stuff that I'll talk about is this. Another name for it is proxy. So this stuff is automatically created when you register this function. Okay, or this method. This is a method of the object. Okay, the last one is the middleware. Okay, this middleware is buy from some company, and they create for you ready-made middleware, so you don't have to worry much as well. And the middleware will have everything inside pre-packaged for you. Okay, and it can communicate in the same way as RMI and RPC as well. Okay, so basically, it's a group of RMI, RPC pre-made for you. If you are talking about this just now, you have to go and register this. That means you need to know about RMI and RPC. But when you use the middleware, everything is done for you already. Some other programmer designed for you, and then sell it as a package. You buy it without you needing to know what to register, and then you just call. As you call, it will do the same communication, and it gets job done. Okay? By using this middleware, everything becomes transparent, meaning that even though your processes run on different server, but then on your machine, you just invoke it just like a normal function call. Okay? Minus the step of registering this this function inside the RMI or RPC services. Okay, so I think that's all for this. I'll move on to the next slide, which is lecture 3. Slide 3 is on memory management. We'll talk about shared memory. Simple memory first. Shared memory, distributed shared memory, and memory migration. The first two there is actually a centralized memory management system. And then the last thing is related to shared memory, which is distributed across multiple computers. Okay? So as your program gets more and more complex and needs more processing time to accomplish the job. You don't solve it using a single computer anymore. You need multiple computers to do it, right? Because we cannot scale vertically, but we can scale horizontally, okay? Of course, if we can scale vertically, we can do so. We will do it, all right? But we already reached certain physical limit for silicon, okay? That's why you can see that the processor speed does not increase anymore. In the past, in one decade, I think we increased about 1,000 to 10,000 times. Okay? We start from kilohertz to megahertz to gigahertz in a very short time. But for a very long time, we cannot get past this gigahertz. We cannot go to terahertz. Okay? The reason is because there are many physical limitations, right? Dealing with the speed of light and all that. So we have reached the what do you call it? The last mile of our silicon capability. So that's why everybody is looking into quantum computer right now. Because quantum computing, although the idea is different, the way we program is different. We cannot think the way we program like this. It will not work. We have to think differently, very, very differently, in order to harness the quantum computing. And one thing good about quantum computing is you can actually process it and it can compute everything at the same time, right? Everything at the same time until when you read the data, the system will fall into one solution. Okay, this is something kind of weird. Quantum computing, even physicists also don't understand it. What happens is this: if in quantum computing system, quantum world, if you don't observe it, it actually appears in many states. Okay, you can only guess the probability. You can guess, okay, it can be this state or it can be that state, but you cannot be sure what it is. So it can be in all states at the same time. So it's good in quantum computing because if it can be in all states, it means you have all the solutions at one time, right? And when you start to read it, it will fall to one solution. Okay, when you fall to one solution, it will be a definite answer already. You cannot be in quantum state, in this probability state anymore. All right. So one thing good is because it already in many states, you already have the solution. When you start to solve the problem, you already have the solution. Just that when you start to read, you fall to one solution. So it's very, very fast, right? And one challenge, there are a few challenges. One is how do we program it? Because we have to think differently. We cannot program just like what we program now. We have to program in a very different way. Second thing is we still have problems like, for example, how to operate it, because you have to operate in, currently the material that we use, it has to operate in sub-zero degrees Celsius because of noise, right? So the temperature that we use for quantum computing is minus 200 over degrees Celsius. Okay? That is the temperature in space. You go to space, you will freeze to death because of this. Okay, minus 200 over degrees Celsius. Okay, the reason why we have to reduce to that temperature is because of the noise. Okay, if the noise is too large, we cannot read it properly. So we have that challenge. So that's why you see the system actually have the tubes. You see metallic tubes, a lot of tubes, right? That tube actually carry the gas. The gas is to cool down the chip inside that, which allows it to operate at a very cold temperature. Okay, that is another story. Let's come back to this. Okay, as computing tasks get larger and larger, and we already reached the last milestone of the silicon, unless there is some discovery in order to improve the speed. But we for sure at the moment we cannot scale vertically, so we have to scale horizontally. Scaling horizontally is like this picture. You cannot have one computer and try to improve the efficiency again and again until forever. No. You have already reached the limit. Right now you have to scale horizontally. So if you scale horizontally, that means add more computers, and you have to network them together. and that is the topic of distributed system. Okay? So in order to solve the task, we solve it using parallel computing. And because we scale vertically, so we have to do it distributed computing, right? So distributed computing and parallel computing is together, is because of this. Right? We want to do parallel computing, we cannot scale vertically, we have to scale horizontally. That's why distributed system comes together. Okay, so we have a problem which is larger and larger. Like for example, if we talk about AI, the data that it needs to process is in petabyte. Okay, gigabyte is 10 power of 9. Right? Terabyte is 10 power of 12. Okay, and petabyte is 10 power of 15. Okay, that means 1 follows by 15 zeros. That's quite a lot, right? Of course, it's still increasing. And if we talk about training, for example, training AI, you need that much of data. Otherwise, you are not able to train the AI well. So you need a lot of data in order to process it. Well, how are you going to process it in a short time? Okay, and also you need more memory, right? So you need bigger memory, you need bigger storage. You also need faster computer. But if you cannot scale vertically, you have to scale horizontally. You increase by not running on a single computer that is faster, but run it in parallel. Okay, that means you have reached the limit, it's fine, but then you distribute the task and you run them in parallel. Right? And you do it with, in order to solve this, you do it using many computation simultaneously, at the same time. Because of the horizontal scaling, that means we have to have some kind of memory sharing, right? But before we go into memory sharing, let's look at the memory management system first. Now, in memory management system, actually this one is not so related, but I think I can touch it. Let me look at the other slide first. Okay, I talk about this one first. Then we'll come back to the previous slide. So we have simple memory model, the computer, the memory. Okay. In this case here, we don't have virtual memory. Virtual memory, I'll explain to you later on what you need there and why it exists. What is the benefit of it? In simple memory, we don't have virtual memory because virtual memory, we want to include it, is very complex. And we also don't have caching. Okay? You all know why you need caching, right? I already explained to you in practical, right? Caching is required. It's actually a duplicate of memory inside your external memory, which is smaller than external memory. And the reason why you need it is because you want it to be fast. You want to access it fast. You want the data that you use often, you want to use it fast. Or the data that you predict you're going to use in the near future, it should be in a cache. So that when you retrieve it, it will be fast. Okay? Because of the physical limit of the speed of light and many other things. Okay, so that's why you need caching. But if your simple memory don't have cache, then you have to suffer. Okay? Because everything runs very fast right now. In the past, of course, we don't have to talk about cache because everything is run in kilohertz and megahertz. Okay? So in the past, we don't have to worry about cache. But when we reach this stage now, we have to use cache. Okay, so it's a bit more complex, and it's no more simple memory. Okay, let's get back to another one, which is virtual memory. Okay. Or maybe I'll go this one first. Shall I? I go to here first, because I kind of forget to talk about this. Okay, this one is not really related to what we're going to talk about, but I think I have to explain a little bit about virtual memory. And you have learned this virtual memory somewhere, right? If you learned cache before, you must have learned virtual memory, or touched virtual memory in some subject, right? Okay, what are virtual memory? Why do you need it? What is virtual memory? Temporary
temporary memory, virtual memory, temporary memory. Sounds like cache to me. Okay, virtual memory, what do you need? If let's say, for example, I have limited memory. Okay? Limited memory. I only have 4 gigabyte of memory. Okay? Maybe to you it's some of you is big, some of you is small, right? But suppose I have only 4 gigabyte memory, but then I want to make my program see the memory bigger than that. What should I do? Virtual memory. Okay, so virtual memory, that means I fake to allow the program to see that I have more memory, but actually I don't. I don't have that memory. Okay. Why is it important? Okay, let's talk about slightly smaller memory, just to give you an idea. Because I know that I thought too big memory, maybe you say, oh, that memory is actually quite big already, but why do you need so much memory? Okay. Suppose you have a very small memory. You got only you got only half a gig, 500 megabyte memory. Okay? But you want to make your computer, your program to see that you have more than this. You have 4 gigabyte, let's say. That means you want to make your program see that you have how many times? 8 times. 8 times more than what you have. Right? Okay? And you use virtual memory. Okay? Why? Because maybe you have something like this. I have my program, let's say memory 0 here, 4 gigabyte here. My physical memory is up to this point, right? Okay? And suppose my program, when I run it, my program can be very big. Maybe it takes up 300 megabytes. Okay? And my data, where I'm going to put it, my data is even bigger than that, let's say 2 gigabyte. But I don't have memory there, right? What I can do is this. I can take this 200 megabyte. Okay? I take some data. I store all my data inside my hard disk, and I read it, and put it here, and then process it. Put it back into the storage. Take another part, put it, and then process it. Very tough, isn't it? Do you want to program it this way? First, you have to worry about how to solve the problem. Second, you have to worry about how to move up, in and out. If let's say, for example, I need some data at the same time when I do the processing, but I don't have enough memory, how am I going to do it? Very tough, isn't it? Okay, so virtual memory comes into picture is to allow us to overcome this problem. So right now I see the memory as I have this much of memory. Okay? Even though I only have this 300, right? And the process is the same. Now it's going to be the hardware and the operating system do it for you. Okay? So let's say you touch this memory is not available, right? Then the operating system and the hardware is going to make this appear here. So that you can store the data here and then you can read the data, right? So if you are touching the data here, then you take some part of the memory and put it there, okay? And then you can read it and out. But let's say you use up all, then you do the same. You move into the hard disk and move it into here. But then in your computer, you don't see that. You see that you have 4 gigabyte of memory. It's much simpler to program this way, right? So all the hardware is done by the operating system and the hardware. That means the CPU. So CPU hardware and the operating system work together in order to give you this illusion that you have 4 gigabyte. Actually, you don't have it. The advantage of this is you don't have to do it yourself. Operating system and CPU is going to do it for you, like swapping out in and out. Okay? So how does it do it? There's a table. And this table is the linear address. Oh, I don't have ink. And it has a virtual memory address. So linear address, let's call it LA. And that virtual address VA. linear address, virtual address. It has a table there. So this table is going to tell you, if we touch here, where is this virtual, if we touch this virtual address, where is the linear address in this memory, the actual physical address that you have? Okay? So if you're touching this, this memory is this location here. Let's say this is location 0, location 1, location 2, right? So 0 here. And this 0 is mapped to this part. So whenever you touch this, you go into this memory, actually the virtual memory, which is the MMU, Memory Management Unit, is going to convert this address into this address. So when you're accessing here, actually you're accessing this address that is available in your physical address. And how does it do the translation? You use this table, this translation table. You always check this table, and if whenever you access this segment of data, you go into this memory. Okay? Now, for example, if let's say now you don't have memory, you have to swap it out, right? So you swap it out, and then you put an X there. So if you touch it, and you see the X, it knows that it's not there. The data is not there. The data is in the hard disk. So you read from the hard disk, and put it there. Okay? Now, it re-enables your program. Now your program is safe. The program will run it. So from your program perspective, it sees that it has all this memory, but actually it does not have this memory. The computer, the hardware, and the operating system trick the computer to think that it has. So that is the advantage. Now you can see the advantage, right? Why you need virtual memory is to simplify us as a programmer without needing to know how to transfer out, in and out, and worry about this limited memory. Because right now, we program just like normal. Okay? And the hardware and the operating system is going to help us do that for us. And this process of doing it requires this paging and segmentation. Okay, they use that, but I'm not going to that. And page replacement operator, where you have to sort in and sort out. Okay, but I'm not going to that. I think some study that you have done before talk about this, right? For example, memory thrashing. I'll cover that also in page 4. Thrashing, you see that? Memory thrashing in page 4. Okay, so that is talking about the memory, virtual memory. Let's get back to this. So we have simple memory where we don't have virtual memory, we don't have cache. That is for computer that is slow. But as things getting faster and faster, of course, we cannot eliminate them. That's why you have to bring in virtual memory. You also have to bring in a cache system. Okay, as systems get more complex, require more data, and also the speed is getting faster and faster. So we have to bring that in. Okay, so the next thing is that is not enough because we are talking about on the single computer right now. We are talking about distributed computing. We have to bring in more computer in order to do horizontal scaling. Now we have to deal with shared memory. Okay, in shared memory, you can share among computers. You can also share within the computer itself. Okay. So you will need to know, you need to have inter-process communication between the processors. How do you communicate and share this memory? Okay, and multiple processors share the memory location, which can be local memory, which is local cache, physical RAM, or secondary storage, or the memory that is outside the computer. Okay. Okay, so Intel processor, because every modern computer will be running at gigahertz, so you cannot avoid this level 1, level 2, and level 3 cache. Sometimes you have even level 4 cache. Okay, because of the speed and the slow external RAM speed, we have to have the internal cache like this. And why do we need to have level 1, level 2, level 3? Okay, level 1 is the fastest of all. Level 2 is the second fastest, level 3 is the third, and the fourth one is level 4, right? So the level number actually tells you their speed. And also the organization. Level 1 will be very close to the CPU. Level 2 is further away, level 3 is even further away. Okay? The reason of the speed of light that I was talking about. Okay? And the way that they implement it as well. Level 1, it needs more power, and the memory actually need more space because they use different technology to produce level 1 memory. Level 2, something similar to level 1. Level 3 maybe is a little bit more different from level 2 and level 1. Okay? They might be using different technology because of their size. So level 1 normally is small, so you can actually spend more or spend more in terms of space as well as power. Level 2 also is slightly bigger than L1, and normally L3 is the largest one. Okay, so we try to minimize the size and also minimize the power consumption. So the technology is for L2 is slower than the rest. Okay, because of that. But of course, it's much faster than the memory outside, which is double. Okay, what are the things that we have to worry about? Not only in distributed computing, but on the same computer, we will have this problem called bus contention. Okay, so you have one computer, but then you can have multiple CPU, right, or multiple cores. So one computer, you might have core 1, core 2, core 3. Core 4, let's say. And then you have memory in between here. Maybe this I call it too small. It should be the largest of all. Okay, and they need to grab the data and store the data in this memory, right? So we have bus contention here. For example, I grab it, and now you also need to grab it, and I change it. You also want to change it, so you have bus contention. Someone has to wait for one another, right? For example, you want to go up the bus. The door is that size only, right? Although the space inside there is big, but you have to queue up, isn't it? It's the same thing here. So even though you have multiple cores, you try to access this data, you have to queue up also. So you have bus contention, right? So this bus contention can be the bottleneck or the shared memory, right? So if you have multiple cores, if you share the memory, it's not ideal to have bigger than 32 cores because if you have bigger than this, normally you have so much penalty of queuing up, and therefore you don't have any advantage of having multiple cores because everybody has to queue up and wait for one another. Okay, so normally the number of cores is less than 32. Okay, if it is more than 32, like GPU, you have a different architecture, and you need to program it in a certain way. Okay, so you have to follow the rule. In general purpose computer, everybody don't follow any rule. So definitely you have bus contention and you cannot avoid it. Okay? For GPU, you can increase like 1,000, 2,000 because we have to follow simple rule. Okay? That rule is given in the library. Okay? So sometimes you can touch it, sometimes you don't. You just put in the data and then the library will handle it for you. So you can optimize for you. Okay, in the shared memory, the performance is an important issue. Issues like how you're able to scale, okay, without sacrificing the performance. You want the performance to be better or stay the same. And also, you need the data to come, and when you need it, it's not like you have to wait, right? Okay, and most of the time, the problem with real time is because things are overlapping. So somehow you need to wait, right? So you need to wait to actually do something to it so that even though there's overlap in communication and computation, you're still able to do things in parallel, right? For example, you can use prefetching of data in advance. Like for example, cache, you prefetch it because you know that you're going to use immediately in the future. You prefetch it before you use it. Okay, and normally you will have a non-symmetric kind of way memory arrangement. Okay, we will talk about it later on. Where you got a local memory. Now, for example, here you can have local memory inside core 1, which is not visible to C2, C3, and C4. This one is shared, but this one is local. So you copy it over and then you use it over here. So you reduce the bus contention, right? You prefetch into here, and then you use it here. The same thing, you prefetch and then you use it. Of course, you have other problems like, for example, consistency. Because you copy and you change here, but this guy doesn't know that you change, right? Somehow you need to update, and this memory need to tell, okay, something has already changed, you have to read another time. So how do you overcome this? There are a lot of problems there. Okay, so when you share, most of the time is this kind of issue, and you have to solve this. All right, so we can have a large symmetric multiprocessing system. Symmetric means the memory is shared equally. Yes, that is symmetric multiprocessing. Asymmetric multiprocessor means the processor has different memory, okay, and the size and the access speed also different, right? And that one is asymmetric multiprocessor. But how does the C2 access the data inside C1? Because it's asymmetric, right? You can actually request from C1, and then C1 will pass it to C2. Of course, you have to go through this kind of communication, right? So there are issues, and there are a way to solve it, and there are many other ideas that pops out in order to solve certain problems. Like, for example, sharing in an asymmetric way. Okay, one of the main problems of shared memory is race condition or data races disadvantage. So that's the main problem. And OpenMP actually has some features available, like for reduction that you've seen before. And that actually helps you solve the problem without you needing to do it yourself. Okay, you do it behind the scene. And we will cover a risk condition in more details in chapter 4 and 5 together. And you'll see how actually it is done. Okay, you can do it explicitly yourself, or you let OMP do it for you. Of course, OMP do it for you is much better because it's much simpler on your side. Okay, so this one shows you the shared memory computing. You can have one process. Let's say this is one process, right? And you got multiple threads here, and they share memory, but they don't share step pointer and program counters and register. This register and all that will be their context. Okay, so you need to context switch as you go from one thread to another. Okay, so this is one process maybe. We call it process ID, user ID, group ID, files, and log and socket. So that data is belonging to the process. And by having these threads, actually you can save quite a lot because you don't want to do multitasking using processors, because switching from process to process is very heavy. So you might want to have one process, multiple threads. And this thread is going to execute them maybe concurrently, maybe sequentially. Right? Concurrently if you have multiple cores. Okay, and then you can utilize this using OMP, because OMP can help you utilize the cores by creating multiple threads and assign the threads to run on different cores. And you don't have to worry about it. Okay, just like when we run this OMP program, we don't even know how many cores that we have, right? We don't even need to know how to program the core even. So the OMP will do it for us, right? So it will handle all these difficult tasks of knowing all these threads, how to do task switching and all that. You don't have to worry about it. Okay, the OMP will help you do it. Okay, this one is basically just showing to you some code on how to do first exposure to by right now. First exposure in lecture on how to do parallel computing using OMP, OpenMP. Okay, here is there any reduction? I can see that for reduction. So R is the shared data, and it can face race conditions. That's why it is inside. Okay. Okay, so just now I talked about the shared memory, which is on a single computer. Now we switch to distributed shared memory. And in distributed shared memory, as you know, is because when we scale vertically, of course, horizontally, we need to communicate between processors that is running on different computers, right? So you need to share the memory across the computer, okay? Because you might want to process on certain part on certain computer, and when that is done, you want to process it on another computer, you have to move the data across the network. So you have to figure out whether you want to process on the same computer or you want to move it away. And you have to consider the overhead as well as you do so. Okay? And of course, all this requires you doing it yourself, or you use the library to do it for you. And this distributed shared memory need to maintain the communication, making sure that the data is consistent as it goes across multiple processors in the same application. Right? And we can use OMP or MPI to actually help us develop the software much easily. If you do it yourself, I think it can be very, very tough. Okay, so when you deal with the distributed shared memory, you have to think about how you want to distribute the shared data. Okay, do you want to cluster them on a certain part and use the resources at that part to solve the problem, or you want to distribute it and you have to look at the overhead and all that, right? And you also need to know how many threads of process that is reading or writing into the shared data, okay? Because this can have an impact on race condition as also the speed of your processor, okay? So you might need to adjust your program slightly. If let's say there's a race condition, because you're programming this way, so you have to change your programming style. And this one we will cover later in later chapters. If you see a certain program is written a certain way, you can actually adjust it so that you don't encounter the problem. Okay, so we try to mitigate this kind of problem by rearranging the way we execute the program. Okay, we will cover more details later. Okay, so when you share the data, you also have issues like, for example, do you want to do migration of that data or you want to replicate it? Okay, so it depends on your application. You do migration if, let's say, you want to conserve the memory. You migrate it to another system and then you process it at another place. And why do you need to do so? Let's say, for example, right? You can have, I give a silly example. Of course, you can think about much better example by give you one silly example. Suppose this is my computer, I invest a lot, and it has no GPU in it. Okay? And this is another computer, another server farm somewhere else, it has GPU in there. Maybe this one is in Japan, this one is in Indonesia, let's say, for example, right? I got a very large server farm here, very large server farm here. Now, if let's say my application, certain parts need to process without GPU, some require GPU, okay? Maybe this with the GPU, I have very less limited resources. But here I got thousands of times bigger than that. Most of the time I will be solving here in Indonesia, right? But there's a certain part that needs GPU. So I have to migrate my data, right? So that the processor can process it. Okay? So maybe my migration here, I look at the overhead. The overhead is lower than the advantage of the GPU process in parallel. I can get the data faster and we offset this overhead. Then I'll rather migrate it. Okay? So this is migration because the data is migrated. Get copied over and get deleted here. We do not need it here anymore because the data needs to process it. Right? And this data may be migrated back, the results may be migrated back. Right? So that is migration. Now, how about replication? There's another way to distribute your shared data by replicating. Okay, this is one example for migration. Let's look at replication. Let's say this is, I think I've talked about it before. This is a Netflix server in the US. Okay, and I have video for all the movies. In Asia, let's say I got 10,000 people watching the same movie. You don't want to stream this 10,000 connection to US, right? Because along the way, it's going to halt the network with this 1,000 requests of the same movie. What you want is to replicate one copy here. In Malaysia, because it's Malaysian, replicate, we transfer only one time. And then here, you can have 1,000. Because it's nearer, it will not affect the backbone of the internet. Okay? So this backbone here is high speed, but then it's limited, right? Because there are many traffic that is going through this backbone. But on this local network, you might have 1,000 this method. So here you do replication because you don't do migration. If you migrate, that means this copy is gone. That's not ideal, right? Because some other countries, like Canada, Europe, also want to watch. You have to download from the main copy in the US. So here replication is more suitable. Understand? Okay, so you have to look at how it actually is used. In this case, we want it to be migration. In this case, we want it to be replication. Right? Okay, another thing that you need to consider when you do the two is whether you will face trashing. Okay? What does trashing mean? Trashing means this. I copy over, do the process, I have to copy back. Right? I have to copy back again and again. So this kind of process is called trashing, because I have to go back and forth, back and forth. The data needs to migrate or copy over back and forth. Okay, so this is trashing. Now, trashing can be avoided by maybe sacrificing a little bit. Don't use the GPU, use the normal without the GPU if you can do it. Okay? If you can't, or you want to save still, you might want to migrate some of your asset into Japan. Okay, this one will be moving an asset to here. So instead of just limited GPU, you might have, without the GPU computer, farm here as well. So that you don't have to move back and forth and cause this crashing. When this crashing is bad, because why? Because you're going to use up this bandwidth, which is the bottleneck between Indonesia and Japan. Okay? So because it's long distance, right? And then a lot of people are using this network. So this is not desirable. So you have to relocate your asset somewhere. Okay? If you cannot do it in the software, you have to do it physically. The next thing is you have to select the block size. Okay? How big is that block that you copy over? And this block size is something to do with hardware limitation. For example, just now I was talking about virtual memory, right? And I show you one box copy over to the hard disk, secondary storage, and come back again. For example, you do sorting, right? And that is actually paging. And that page is the page size. And that page size is determined by the CPU. And you cannot change it, right? So the block size here can be the same issue here. So your system might have this kind of limitation because it's not viable to transmit only 1 or 2 bytes. Normally you don't transmit 1 or 2 bytes, you transmit one whole block, right? So you have to select the block size, okay? And this block size also will affect your decision on how big is your data that you want to process at one time, okay? So that will be your block size selection. Yeah. as I said before, you don't want the whole head to be big, right? Because if you transfer 1 or 2 bytes, that is going to be a big overhead. So you transfer one block rather than 1 or 2 bytes. But then, of course, when you transfer block in block size of certain size, you need to make sure that you change the program so that you process it in that kind of block size rather than in byte size which is smaller. And then you have to worry about, or you have to think about the location of data, like what I mentioned just now. If you know that your data is here, you better put your compute asset here rather than in somewhere else. Okay? If your data is there, make sure that you have the asset there. Otherwise, you have to copy over and then it can cause crashing. Okay, and then this part is actually talking about the shared memory location, basically where you put your memory. Just now, it's actually talking about the data. Okay? So you put your memory or your compute asset at the specific location so that you don't have to migrate your data or replicate your data often. Okay, how do we do it? We can do it using those libraries that I mentioned to you. OpenMP, in this case, is distributed memory. OpenMP is not suitable. We use MPI. Okay? Or you can use a different way to do it. Right? Or if you want to do it yourself, then you have to explicitly package your data and send it to the cluster to process it. If you use MPI, okay, this one is done by the MPI. Of course, the program will decide what to send, but the major bulk of the heavy work is done by the MPI on the transfer. Okay. Okay, because we want to use MPI rather than doing it ourselves. So let's look at a little bit of background about MPI. Okay, MPI is a message passing programming model which coordinate the processes that is running on multiple computers or single computer. The main advantage of MPI is on multiple computers. Okay, each process has its own data, and the data is exchanged by sending or receiving messages. And the programmer used this the library to build this multi-computer, which is horizontal scaling. Okay. This is one simple example. Okay, these are the shared data on different processors, and this process can run on different computers. And this data here normally want to be on the same local machine because in order to compute it, you have to use this data next to it, right? And this data is replication of the same data. And of course, you have to maintain the consistency. And if I change the data here, I need to make sure that the copy also changes. Okay? So when you do replication, these are the constants that you have to do. When you do migration, it's simple. When you migrate, the data is deleted from the original source, and then you go to the destination, right? But when you do replication, you have to worry about consistency. Okay, when you do MPI, these are the functions that you use, and you will see this in practical. You can use send and receive, and you can use asynchronous send and receive as well, with the I attached to the front. Okay? If it is prefixed with I, it means that there is asynchronous send and receive. I think there's some example talking about the asynchronous and synchronous. Is it? Yeah. Down below. I'll explain later. Okay, so the MPI is a standard library. It's pre-programmed for you. You don't have to worry about programming it, and it is highly active. Every year I see this MPI has newer and newer version. Okay, so it's very active. It's good. It's a sign that it is good because there's a lot of contribution and improvement in this MPI standard library. Okay, and it means that a lot of people use it. Okay, and it's ubiquitous, that means it's everywhere because it's free. You can download it. Alright? Microsoft has its own version. You can download it from Microsoft free of charge. And it's used in high performance technical computing, especially in universities. Of course, in universities in America or European universities, they use it for their research. Okay? Whenever they need to scale horizontally, they use NPI. Okay? But of course, this is not the only solution, but this is one of the popular ones. Okay, nearly every big academic and commercial simulation data analysis use this, as I said before. If you go to a research paper, you can see a lot of those deal with the distributed and probability. They use NPI directly or indirectly. Directly means they use it the NPI directly. Indirectly, maybe they are using middleware, where they buy a package. The middleware actually helps simplify the programming for the developers. Okay, so why do we need to model with the NPI? Okay, can't we use low-level network libraries like Socket? Can, if you want to, but you will suffer. Okay, because you have to develop, you have to test, you have to make sure that it's working, right? We use MPI because this is tested, and it's used by the university. Always they get feedback from the universities, those people who use it, how to improve their usage. Okay, so they optimize for performance, and it's already done for you. You don't have to worry about it. So it's a good idea to use it, and I suggest that you use this MPI if you don't have an NVIDIA GPU. Use MPI or OpenMP to demonstrate your application. Okay, solving it using parallel computing or distributed computing together with parallel computation. Okay, and MPI actually, because they are developed by seasoned programmer, so these people, they know what transport protocol to use so that they can be the fastest. Okay, it might not be the best if, let's say, you use your own protocol to do the communication. You're thinking, okay, I use TCP, but maybe they use UDP, which is faster. But of course, UDP is difficult to program. But these people, they are seasoned programmers. They might use UDP and make it even much faster than TCP protocol. So it depends on how they develop it, right? So these are mature library. So these are the advantages. So they use the fastest transport available without you needing to learn and program yourself. And it's good for industries and also academic institutions. And not only it is used in distributed system, it can be used in a shared memory within a single computer. You don't have to use OMP, you can use MPI if you want to. The reason why you want to use MPI from the beginning is maybe initially you think, okay, I'm going to use within a computer, right? So you use OMP. But if you want to scale vertically, then you have to use multiple computers. You cannot use OMP anymore. OMP can do parallel computing on a single computer with multiple cores. But if you want to use, you want to scale vertically, you might want to start with MPI straight away, right? So MPI, you can do within a single computer. If you want to scale that, you scale easily because you don't have to change anything because you're using the library, right? So what you need to do is you create a list, you tell the node, the IP address, and then you just start the MPI, and then the MPI will go and find out how to distribute the data, okay, and how to process it, how to gather the data back, right? Of course, the certain part needs to be programmed, but a lot of the heavy lifting hard work is done by the MPI library itself. Okay, and then you don't have to worry what kind of medium that you use. Okay, of course we all use Ethernet, right? Every time or Wi-Fi, you know? But if you go to companies, they might not use Ethernet. They might use InfiniBand. They might use MicroNet. They might use different kind of technology from IBM, even faster than Ethernet. okay, or more reliable. So if you have to program yourself, then you have to go and learn, right? But if you use API, it depends on what you have, what network that you have. Maybe you have infinite band or myriad, then it can adapt to it without you needing to program it. You don't have to change the program anymore. Okay, so this library is going to help you make this communication medium transparent to you. Okay, you do not need to know how to program this infinite band. Okay, so it will use all this faster version of it. Okay, but of course, if you cannot find it, you'll fall back to TCP/IP because TCP/IP is the most commonly available, right? Even your PC, so you got Wi-Fi, you got internet, it's TCP/IP, right? Okay, so if everything else fails, that means everything else not available, you fall back to TCP/IP. Okay, so this is done by the API programmer and the library. You don't have to worry about it. Okay. Whichever network, whichever protocol that they use, is they decide and they optimize it for you. Okay, another thing about API is this, you don't have to worry about the messages that you send. It can be, the network can be unreliable. For example, Wi-Fi or maybe even worse, not Wi-Fi that you use. It can be satellite link, which does not have a reliable message transportation. And you don't have to worry about it. If you use UDP, you have to worry. Of course, if you use TCP, you don't have to worry because TCP will do it for you. But if you use UDP, then you must make sure that you have to resend the data. You have to go and find out whether the data is lost and then resend it. Okay? And then you have to do timing as well. For example, the data is sent, and you wait, it doesn't come back, and then you have to send. You have to send at specific time because you cannot wait too long, right? So the decision to wait or not to wait, you don't have to worry about it, right? Because MPI can handle it for you. Of course, you can say that TCP also can handle it for me, but here they will find the best solution for you. If all else is not available, they fall back to TCP, of course. But they might not be using TCP, as I said. They might be using UDP, which is not reliable, but they have some protocol that is fast enough to compete with TCP available in this library. And you also don't have to worry about in-order arrival that is, actually it's not in-order arrival, it should be not in-order arrival of the message, okay? Because when you send the data, right, let's say for example, you send to the internet, okay? Although the internet looks like a cloud, but actually it's not just one path to get to the final destination. For example, let's say this is a Malaysian network and this is America. We want to go to America. We can go through Thailand, European Union countries across the Atlantic Sea to America, US. Okay? Or we can go through Japan, through the sea, and then to the America, the other way around. Okay? So if your packet take this path, it might be different than the packet that take this path, right? I mean the time. Maybe this one is shorter than that, right? But if I send this one first, send this one later, but because this is shorter, this packet might reach first. The second packet is sent might reach first. So it might arrive not in order. Okay? So how do you reorder them? If you use UDP, you have to worry about it. But if you, of course, if you use TCP, you don't have to worry. But if you use API, it's even better. You don't have to worry at all. Okay? Because it's handled for you. Okay, why we have to worry about this? Because when you send the data, we cannot send 1 megabyte of data one shot. You have to chop it down into packets. They have a limit. The packets has a limit. You have to send them in packets. So you have to chop it down and you have to send them packet by packet. So they can arrive at different times. Okay, so it's a protocol, communication protocol needs to be able to reorder them back into the correct order at the receiving end. Okay? Okay, so that is the enforcement of the certain guarantees. And next is when we design, we don't have to know technical computing about multi-node. Okay? Because MPI will do it for you. You just list down the node that is available. Okay, and then you will go and distribute it for you. Okay? And it's completely standard, it's available everywhere. The library with the documentation is there, and it doesn't change much. There might be a new feature, but the old feature is still there, and it doesn't change. Okay, so it's pretty standard. Once you program one time, if you know how to program it, then it's much easier to adopt this as a solution rather than creating your own. Okay, it's a specialized routine collection of operations which can help you do a lot of things. Like just like, for example, OMP, right? If I did not show you for reduction, you would not know that it's as simple as that, right? Because if you were to do it yourself, it's very hard, isn't it? But before reduction, it's so simple. So the same thing for MPI. It comes with a collection of functions that you can use to simplify your operation. Of course, this has been optimized and requested from the user. And the user before us, they already requested from this committee, and they already implemented for us the one that is useful. Okay, so this is the MPI example. We will do this in one of the practicals. First thing is we set it up, or how to shut it down. To set it up, we use MPI unit. To shut it down, we finalize, MPI finalize. Okay, you will see this very often, just like OMP, where we get the ID, right? And the size of the number of tracks that we create. So in this case, also the same thing. You want the size of the tracks, you put MPI time size. If you want your ID, you check the rank. They call it rank, actually rank is the ID. It's similar like ID. And then when you send a message or receive message, you use MPI send, MPI receive. Okay, this is unlike OpenMP. OpenMP, do you send any message? No. You only share the data, right? Okay, so sharing data, you don't have to send message. But in this case here, you have to send a message explicitly, even though it is on the same computer, right? So the disadvantage of this MPI is this. Because you have to send a message, you need to copy that message and send it over, right? Whereas OpenMP, you share the data. If you don't send the data, you put the data in the memory, and then you tell the other process, the data is here, by passing the pointer, and then you just process it using that pointer. So it's much faster. Okay, so OpenMP, the advantage is that. MPI, the disadvantage is this message passing. But this message passing will avoid race condition, right? Because you make a copy, so nobody is going to share the data. But of course, here you have a problem. Like for example, consistency. When you share the data, you change, the other side will not know that you change. Okay, because it's not visible. You make replication, right? So this will be a little bit problem. But it depends on how you solve the problem. Okay, you might want to change your processing a little bit, so that you don't have this kind of problem. So is the MPI is the only way to do this computing? Actually, no. There are many ways to do it, but this one is the most popular one, and also it's free. Okay. This one example. I think this one is Hello World as well, something like that. Okay, so you get the rank, which is your ID, and the size. That means how many tracks that is running at the same time. So that is the size. Okay, so you init, and then you finalize when you're done. Okay, right. It's the same as OpenMP. You see, there's only one main, right? So if you're thinking one track is running, no. When you talk about MPI, all the threads is going to run this main program. Okay, they're going to run this main program, whether it is on the same computer or different computer. Okay, all the process running on different computer, it can be very distant, like for example, one in America, one in China, the other one in Malaysia. But if you use FPI, all of them will be running the same program. Okay? Okay, this is the result. Hello, I am 0. 0 is the ID of 2 because the group is 0, 2. Okay, you use FPI exec to launch the process on your computer, and you can also launch it on the remote computer on your same computer. Okay, you run the process on the computer, and you also can initiate the process on another node that is within the same group. So each process runs the program hostname, and each run independently. Okay, they can do the same thing, and the performance usually depends on how many processors or cores that you have in a system. And of course, your FPI will choose the best. You use as many cores as much as possible and processor as much as possible. Okay? To make the processing faster. Okay, the only difficulty when you program is, of course, if OpenMP, you have to add the pragma, right? So that may be not so convenient. Your existing program don't have pragma, you have to add pragma if you are using OpenMP. And then compiler plus runtime system arrange for the parallel execution. Okay. Maybe this one is not so problematic because we use the Visual Studio. So Visual Studio actually hide everything of this. But if you do it yourself, this can be quite challenging because you need to compile and then you need to know how to run them. But for us, we don't have to worry because Visual Studio do it for us. Actually, we don't have this kind of problem unless you do it manually. Okay. And the painful thing is it relies on the shared memory, so you cannot do it in parallel for multiple computers. So this is a limitation. If you want to use OMP but across multiple computers, you have to do your communication yourself to different nodes. Okay? So what is the painful thing about MPI? You must rewrite the program to describe how the multiple process do it. So you have to convert your single process into multiple process. Okay? And you have to explicitly move your data using send and receive. Okay? And what data that you need to send, you have to specify where to where. To where means to which ID, okay, or which rank that you want it to process. Okay, you don't have to tell the IP address, but you tell the rank, which is the ID of the threads. Okay, the only advantage for API is it can operate on systems that don't have shared memory. Like for example, I have only network, I don't have shared memory. I can use this API. Okay, for FPI, I mentioned to you already, the size is actually the number of processors and the number of threads running. The rank is the identity, the ID of your processor, the thread that's running. And this is the function that you use in order to get that information. Okay, this one is to compare the frameworks that is available. you have multiple processors with MPI, and this is a fixed number of processors that's created at the program start. And all processors is going to run this main. Okay? That's why your main is the one that you program, and you need to tell the processor what to do, okay, by using the ID. And they run on isolated address because they don't share memory, right? So you have to share the data by message passing. Okay, the multiple processors use fork. The one that I mentioned to you just now, fork. Processors created using the program execution, and it replicates the address space upon creation, but then it is isolated. Okay, so you use fork, and that is the thing that you get, right? So they don't have shared memory, and that's why you have to send and receive the message. So this is the disadvantage. Okay, and you have multiple threads with P-thread create. You can use one process, but you create multiple threads using these P-threads, or we call it POSIX threads. Okay, this thread is created during the program execution, but then this one is shared. But this one must be on the same computer. This one is can be on the same computer or on a different computer. If it is on the same computer, the memory is not shared. Okay? If you want to share the memory, you have to create P threads inside the processor. But the threads can only see within the processor. You cannot see any data or memory in another processor. Okay? Okay, multiple threads with OMP. You set the thread at the beginning, conceptually, and you use this pragma OMP parallel in order to execute them in parallel. And the data is all in shared memory space. So in terms of data, you don't have to worry about sending and receiving, and it's more straightforward. So this is the frequent differences and advantage and disadvantage. Okay, for MPI, because you need to send and receive, and there are two types of sending and receiving data. One is synchronous, the other one is asynchronous. What does it mean by that? Synchronous means when I send data, I will wait until I get the response. So I send it. Suppose this is my sender, this is sender, and this is the receiver, right? So if I send the data across, there's the first step, and this function will wait. I call this function, and it will not return from this function until this receiver receives it and send acknowledgement or negative acknowledgement. Let's say fail to receive the data, but it's corrupted. So you might send back negative acknowledgement, meaning that it's failed. You have to resend it. So here you have to decide whether you want to resend or you want to terminate, right? So this is the second step. Now, when you receive this acknowledgement, then only you can proceed. If, let's say, the receiver is not ready to receive the data, it does not receive it. You wait because it has to do some other things. Then the sender has to wait. You might wait forever if this receiver doesn't respond. So this kind of communication we call synchronous communication. It means that you have to wait. Okay? Now there's a problem here. Remember I mentioned if the receiver doesn't receive it, then you have a deadlock. Oh, sorry, you have a lifelock. Okay? Okay, deadlock is something different. Okay, let's say for example, I send. Okay? And this guy also will send. Let's say yes, send, and then receive. This guy also sends in his program. He's also sending, and he's also receiving. Okay? Now, suppose this one start and it send. Okay? This guy start, he also send. Okay? And because it's synchronous, right? So you wait. Why you wait? Because the other side haven't received it. This guy also wait because this guy haven't received it. So they wait for one another. This kind of problem is called delay. You cannot move because they are locking one another, and therefore you cannot progress. It's called delay. And this is the serious case. When you get into deadlock, you have to reboot the system. Okay, or you have to terminate this process, these two processes. Okay, so you can have a potential deadlock. How do you overcome this? You reorder it. You receive first. Once one of them must be received first, and then you send. So that when you send, this guy can respond, acknowledge, and then you proceed. And then when you receive, this guy can send. And when you receive, you reply. Okay, so you just need to reorder it. But if we don't reorder it, potentially it can cause deadlock. And this can be a real problem. Okay? So when you deal with the synchronous programming, it's simple, but it's easy for you to make mistakes and you get into deadlock. Okay, and this is the one that I mentioned to you just now. I've shown you this picture. I showed you step number 1, step number 2, right? So you have to send a message and then you have to receive the acknowledgement before you can proceed. Otherwise, you wait. So that is synchronous sending and receiving. Now, in another way, or maybe a solution to this kind of problem, is to use asynchronous sending and receiving, or asynchronous communication. Okay? So what is the difference between this? Asynchronous and synchronous. In asynchronous, when you send, you don't wait. Okay? So the sender send to the receiver. If the receiver is not ready, you do something else, busy doing something else. But this sender will not wait. He will continue on to do his job. And he can do any other job. Okay? Okay, until this receiver receive it, he will send eventually he will send the acknowledgement. And now when it is done, then you can actually process it further. Let's say you return the result, right? Then you can process it further. Okay. Of course, you'll be wondering, okay, the reason why I do asynchronous is when I send, this receiver receive it, all right? And this receiver will process, and then he send back the data. Okay? Then when I proceed here, I know that this data is returned back to me, I can process it. But here, how do I know? Oh, sorry. How do I know that this is received back? Okay, I'll continue this next week. On this part here, because I've actually nearly finished this slides. Oh yeah, I forgot about Okay, you can leave now. Okay, you can leave now.
Sir, how about attendance?
How do you mark the attendance?
Oh, thank you.